In this video, I'm going to attempt to teach you how to read phase diagrams. They're pretty straightforward. I think you'll find them easy. But let's begin this discussion with a demonstration here. In this flask, you see a clear liquid. That's called cyclohexane. It's an organic compound, obviously liquid state under normal conditions. And we're going to attempt to get it to the trimple point. So let me play the video. What they're doing is pumping the air out in order to create a vacuum. So they're lowering the pressure. And then they're also adjusting the temperature. But mainly this is an exercise in changing the pressure. So you can see here that as the pressure drops, we start having a freezing occur. And then all of a sudden you see bubbles forming. So we have the liquid hexane, the solid that you can see, and there are the bubbles. So all three states of matter are currently coexisting. And it's a dynamic process. It's not like it's just sitting there not changing ever. But all three states of matter are present. Right now we would say that cyclohexane in this demonstration is at the trimple point. Take a look at the phase diagram on your screen here. This is a two-dimensional phase diagram. There are such things as three-dimensional diagrams. Those are a little bit more complicated. So for high school, I think it's more appropriate to look at two-dimensional phase diagrams. Like any graph, these are pressure versus temperature. You have to have two variables. So pressure and temperature are the two that we're looking at here. What a phase diagram does is separate the states of matter for that substance. So if you look at this particular example, the solid is almost always the one farthest to the left. And then the gas is almost always furthest to the right. And then the liquid is scrunched in the middle between these lines. Now, every phase diagram changes a little bit. You won't always see one that has this size of liquid zone. It may be very small, or for some substances it's almost non-existent. So don't get it in your head that they're all the same. But it's always solid, liquid, gas from left to right. Now the lines that you see here are made by graphing the pressure at different temperatures for a substance. We call these phase equilibrium lines. We've talked about phase changes at some point in the past. I don't remember, depends on which class you're in. But when phase changes happen, it's a complex process where you're overcoming IMFs. So there's an equilibrium all the time while you're in a phase change. And there's not just one set temperature for a phase change to happen. The temperature at which a phase change occurs also depends on the pressure you're at. And that's why these curves, or these lines, are curves. That represents that. And so this bottom one here, we see that if we cross this line from solid to gas, that represents the phase change of sublimation. And if we go backwards, it's deposition. So this is the solid vapor equilibrium line. This line here separates solid and liquid, so it's the solid liquid equilibrium line. And if we cross this line, the process is called melting, and if we go from liquid to solid, it's called freezing. Likewise, if we go from liquid to gas, that process is called vaporization. It could either be artificial, boiling, or non-artificial, evaporating, so we just call it vaporization. And if you go backwards, it's called condensation. So those are the 6 phases of matter, or the 6 phase changes that we've learned way back in the beginning of pre-AP. But you can see that those phase changes don't always happen at the same temperature. Now on our lines we do have a couple of important points. And let's scroll down and answer or fill out some vocab here, because understanding this vocab is critical into using phase diagrams for their intended purpose. First definition is equilibrium. If you're in AP, you probably understand equilibrium a little more. But if you're in pre-AP doing this, it's kind of a new term. Equilibrium means when you have a reversible process. it goes back and forth. It's a dynamic process. It doesn't mean you're being still or the process is over. It's occurring even though it looks like it's not. At the molecular level, the process is still going. So for example, if I have water that's normally ice, I can add heat and melt it. And then if I take the heat away, it will go backwards to form a solid. If I'm in the process, if I'm at 0 degrees for H2O, then I am at atmospheric pressure, by the way, then I am at a temperature where I'm in equilibrium. I have a little bit of ice and I have a little bit of water. On the phase diagram, the triple point is a very important point. This is the phenomenon we saw in the video. The triple point is where all three phases exist in equilibrium. Think back to the video. We saw the solid, the liquid, and the gas form of cyclohexane existing at the same time. It is one XY coordinate only. And for us, for this, it's a PT coordinate, a pressure temperature coordinate. And there's only one point where all three exist. Another important point on the phase diagram, let's go back up, and by the way, there's that triple point. It's where all three lines meet. Another important point is way up here. Notice that line actually ends. That's not an abbreviation. That wasn't an accident. That line actually does have an end point. The critical point is the highest temperature that you can still use pressure to liquefy a substance. I could have also defined critical point as the point beyond where a substance only exists in the gas phase. Now, beyond that critical point, some weird things happen, and we don't get a new state of matter. We get, oh gosh, how do you define it? It's sort of a pseudo state of matter. It becomes what we call a supercritical fluid. And those supercritical fluids, depending on the substance, have some really, really cool properties. You will be assigned a reading about supercritical carbon dioxide. I think you will enjoy. But the critical point is very important on a phase diagram. And then a couple of other interesting points. Let's go back to the phase diagram. And let's talk about melting. And let's just assume this is water for a moment. This line right here shows you all the possible temperature and pressure combinations at which you can melt ice. Well, most of you think that ice only melts at 0 degrees Celsius. Well, if it melts at 0 degrees Celsius, that's because there's a definite pressure at which that happens. It's atmospheric pressure. If I raise the pressure up to, let's say, 10 atmospheres, I don't know what the actual pressure is, but we can see this line is sloped so that you actually would get a higher melting temperature if you raise the pressure. But since most of us only see this happen under atmospheric conditions, the boiling point and the melting point that you are used to seeing is for normal boiling point, this is the temperature at which liquid changes to vapor, and here's the kicker, at 1 atmosphere. That's what normal means, atmospheric pressure. Whatever temperature the phase change happens at, atmospheric pressure is normal. And the same for normal melting point. It's the temperature at which solid goes to liquid at 1 atmosphere. Let's do some example questions with a couple different phase diagrams of different substances. The first one is water. I want you to notice before we start answering questions that how the x and the y axis are put together. This is not a standard XY graph. This is done almost in a logarithmic style where you have quite large gaps between your coordinates here. So it's kind of hard to read it in that way. Also notice that this solid liquid line is pointed backwards. That may become important soon. Number one, what state of matter is water in at 10 atmospheres and 300 Kelvin? Well, we just need to find that data point and see where it fits. 10 atmospheres, let's say it's about right here. And 300 Kelvin, let's say that's about right here. So we will approximate that data point to be about right there. So we would find water to be a liquid under those conditions. Number two, identify the normal boiling point of water. Okay, so that would be the normal temperature. So what we do, normal means 1 atmosphere, so we take that line over. Okay, and then we go straight down. It's actually already done for you, the dotted line there. So that's 273. This particular phase diagram is in Kelvin. Number three, estimate the boiling point of water at 200 atmospheres. Okay, so boiling points can always be found on this particular line. This is the liquid vapor equilibrium. So let's approximate 200 atmospheres. That's a good shot. And then let's go over till we hit that line, and then let's go down and approximate a temperature. Let's call that, for the sake of argument, 600 Kelvin. Can ice sublimate at 0.5 atmospheres? So sublimation, we have to cross this line right here between triple point and 0. So if we're at 0.5 atmospheres, that means we are all the way up here. So is it even possible to cross that line? And the answer is no. Because the temperature would require us to go beyond absolute 0, so it can't happen. Let's scroll up a little bit. Number 5. I have 10 mils of water at 0.8 atmospheres and 325 Kelvin. Describe the phase change, if any, that occurs if. All right, I may need to find the best balance here. I raise the pressure to 100 atmospheres while keeping the temperature constant. Okay, so we're currently at 0.8, so about right here. Keep the temperature constant, and let's go to 100 atmospheres. Hang on a second. We are at 325, so let's go find that temperature. So we're currently about right there. So keeping that temperature constant, I'm going to raise the pressure and go up. So no change. We started as a liquid and we stayed a liquid. All right, let's go back to that beginning X there. Let's hold the pressure constant and increase the temperature to 400. Okay, so we see if we go this way now to get to 400, which is about here, we're going to cross that line, so we're going to vaporize, boil, evaporate, whatever. In part C, I keep the 400 Kelvin constant and increase the pressure. So now my new position is here. I'm going to increase the pressure from 0.8 to 120, so I'm going to go up. I'm going to cross that line again, so I will condense or liquefy. Okay, let's try a different one here. This is for carbon dioxide. This one gives us that supercritical area, just as an FYI. I have a piece of dry ice at 10 bar and minus 60 Celsius, changing either pressure or temperature, but only one. What specifically can I do to convert it into a gas? So we have different units here. That doesn't really affect it. We have Celsius and bar. Right now at 10 bar and minus 60, I would be at about probably here, somewhere like that. So changing either pressure or both, what can I do to convert it into a gas? To convert it into a gas, I need to get somewhere down in this area here. So I have a couple of options. If I hold the temperature constant, I can reduce the pressure and cause sublimation. So I can sublime at constant T by lowering P. Or I can keep the pressure constant and increase the temperature, and then I can go from solid to liquid to gas. So that's going to be melting and vaporizing by increasing T at constant P. Our final phase diagram is for nitrogen. Notice that in this particular phase diagram, the liquid phase is very tiny. That's our experience with nitrogen, and the gas phase is actually huge. Given acceptable pressure and temperature for solid and gaseous nitrogen to be in phase equilibrium together. Well, think about where is that on a phase diagram for solid and gaseous to be together. That's going to be on the equilibrium line that separates those two phases. So any answer here, you just, if I want to pick 10 psi, come across, go down, and give your best estimation. Let's just call that, I can't even read it, it's kind of blurry, minus 100 Fahrenheit. And on these, I found pictures of phase diagrams with lots of different units. So you would know that units are variable on this type of thing. Number 9, can nitrogen exist as a liquid under atmospheric pressure, 14.7 psi? Well, that's right here. Is it possible? 14.7 psi, the isobar for that would go across the entire thing. And that line never intersects with the liquid phase of nitrogen. So the answer here is no. Under no circumstance can you have nitrogen, liquid nitrogen, at atmospheric pressure. And then finally, number 10, this is kind of an all-encompassing question. Notice the solid liquid equilibrium lines for N2 and CO2 lean to the right. So this is a bit leaning to the right. Water, if you remember, I pointed out water earlier, leans to the left. What does that tell us about the density? That's really a cool part of phase diagrams. It turns out that when this line right here leans right, that means that the liquid is less dense than the solid. But when it goes and leans to the left, like water does, it's the opposite. The solid is less dense than the liquid. And that's an important characteristic of water, because in the winter, when the ponds and lakes freeze, if the ice just sank, it would kill everything in a lake. So that's an important consequence, and one reason water is such a unique molecule for life. All right, well, that's how you read and interpret a phase diagram. You're going to have your own practice now. If you have any questions, come by and see me and we'll work it out.